And then moving on, the last thing on my agenda here is to show you a bit on performance. So we won't need this. Okay, so
this is the native performance you're going to show on the machine itself, on the StorPool.
Yeah, so we're going to do this from the hypervisor hosts. Performance translates really well through the virtualization layer. Unfortunately, we had a technical issue and we couldn't install the required tools within the virtual machines to show you that as well. But we'd be happy to show you that on a separate one-on-one conversation. Right. So one thing on performance, one thing that's important to understand is this is a scale-out system, meaning that performance you get from a 3-node cluster will be different from performance you get from a 30-node cluster, the second being 10 times larger, right? So with every node you add to the system, you get additional performance because that node is connected with additional network interfaces, it has additional drives in it. So a fraction, so if going from 3 nodes to 4 nodes, a third of the operations that went to the original 3 nodes would now be processed by the fourth, right? And so on and so on. So you can think of performance as scaling linearly up with every added node, okay? So to show you performance, I have this 100 gigabyte volume in StorPool. Another thing is volumes are thinly provisioned in StorPool. So we've prepared this volume by filling it up with data. So it's currently 100% allocated. So it has 100 gigabytes of data in it.
It has been written twice, I see.
Can you repeat, please?
Yeah, the replication is 2, you said, here in this case?
Yeah, in this particular volume is with replication 2. But I'm only going to show read performance now. So that doesn't change anything. So the way data is stored for this volume is we have 1 copy on hard disk drives and 1 additional copy on SSDs. You would, in a usual production setup, you would have 2 copies on hard disk drives and 1 on SSD. All right, so to show you performance, I'm going to take that volume, I'm going to attach it on a particular server. It's currently attached on node 2 as well as node 3. So we're going to take it on node 2. So here it is, and we're going to run the FIO benchmark on top of it. So first thing I'm going to show you is sequential read from that 100 gigabyte volume. So here it is. If you're not familiar with FIO, it's a very popular storage performance testing tool. And I've configured it to do direct I/O sequential reading with 1 megabyte blocks and queue depth of 32. And the kind of read speed you can get out from a single initiator in this specific hardware configuration is something like 2.5 gigabytes per second, right? And to reiterate, what the underlying configuration is, this cluster only has 12 SSDs, 12 SATA SSDs in 3 storage nodes, and they're really low-cost enterprise SATA SSDs. There is nothing special about them. The network in this case is 56 gigabits, but we can easily saturate 2 times 10 gigabit Ethernet from a single initiator. So on a host connected by 2 times 10 gigi, you would be getting almost 2,000 megabytes per second of sequential reading from a large enough cluster, right? Then the performance you can expect out of this whole cluster is about the same. So it's about 2.5 gigabytes per second. And the reason is the SSDs, the 12 SSDs we have in this cluster cannot push more data, simply. That's the bottom line. Then for random reads, and I'm going to do a slightly higher queue depth here just to, okay, let's type 32 first. This is random reads 4 kilobyte block size and queue depth of 32. From one initiator, you can get about 130,000 IOPS. The whole cluster is capable of doing about 200 plus 200,000 IOPS or more. And while doing this, you can see that each of the SSDs will be processing something like 6,000 or 10,000 IOPS, right? And the kind of with a higher queue depth, you can get something like 200,000 IOPS from a single initiator, right? And the last thing I want to show you on performance is latency of reads. So the way we measure latency is we issue one operation and then wait for it to complete, and we issue another operation, which is also known as queue depth of 1. This is the inverse of the latency. So it's 5,000 operations per second, which means that each operation takes, it's this number here, takes about 200 microseconds to complete over these SSDs, this network, the CPUs, everything. So while we perform this kind of huge performance on storage operations, so even in a loaded system like this, StorPool would still take one CPU core for each of the StorPool server services, and one additional CPU core for the initiator services, which can be on the same host, in which case you need 2 cores, or they can be on different hosts, in which case you need a single core on the hypervisors to process the storage and networking necessary to perform this.